So, let's start over. I'm going to talk about quantum mechanical and optical analogies in surface gravity water waves. So let's begin with some brief introduction and some motivation. In 1927, Schrödinger and Kennard began to solve the Schrödinger equation for simple cases. And really the simplest case is the free fall. We take a particle, we put it in space and let it fall freely in a gravitational field. Classical mechanics tells us that this particle will accelerate. Now if we go to the quantum picture description, this particle will not only self-accelerate, it will gain a phase. And apparently this phase has cubic terms, okay, as we can see here. No, nothing works today. There, okay? So we have this cubic term here in this Gaussian wave packet. And apparently this is a long-standing problem. It hasn't been measured yet. And it's been 91 years since Kennard first published this in his paper. And we really wanted to tackle it and see if you can measure it. So in my talk, I will explain why would we want to use surface gravity waves to observe effects in quantum mechanics. Then I will show you the experimental setup and show how we can measure stuff. Then I will show you some recent results on the cubic phase and linear potential and more complicated wave functions called quantum carpets. So let's begin with how we describe waves in hydrodynamics. In hydrodynamics, we have this nonlinear Schrödinger equation. Our laser is really weak. And if we look at a case where the amplitude is really small and the wavelength is really long, we can neglect this cubic nonlinear term, and then we're reduced to this equation. Now these two terms, they're very similar to the Schrödinger equation, and this term, if you explore your imagination a bit, you will see that you can substitute d phi to d tau with some v, and this v is the known potential in quantum mechanics. I will talk here. So we really have this analogy of a wave propagating on the surface of water with some intrinsic conditions, and it's mathematically equivalent to the Schrödinger equation. We're resulting in a new system which has an ability to measure the wave function of the surface of water. This is something we could have never done in quantum mechanics because it's impossible to measure the quantum wave packet in the quantum physics regime. Now in optics, it's possible to measure the electric field, which is also analogous to the Schrödinger equation via paraxial approximation. However, measuring a phase in optics is really tough, and measuring a cubic phase of a particle propagating in linear potential is still an open question in optics on how to do it. Believe it or not, there are several papers published every year with proposals of how to measure that in optics, but there are no successful results so far. So how does our system look like? We have a really big water tank. At one end we have a wave maker that generates waves. These waves propagate along a water tank. We have wave gauges measuring the wave height of these waves. And to induce a potential, we have a pump. Now the flow of the water here is phi. Okay? So if we want to create a linear potential, we would have to accelerate our water with a quadratic dependence in time. And then we will observe an equivalent of a linear potential in a microscopic classical system. However, this system, again, it obeys the Schrödinger equation. Let's look at some simple results. Imagine you have a Gaussian wave packet, you generate it on the surface of water, and then it propagates, and here you can see measurements of this wave packet. So again, you can really see the wave function now in an experiment. Then you can perform Hilbert transform. Hilbert transform is a standard procedure in quantum mechanics. It's a tool to extract the phase from the wave packet. And you can see a simple case of linear phase. Nothing new here. This is just a test of proof to see that we can really observe phases. Let's go to a more complicated case. And this is the case that Kennard showed in 1927. Again, we have a Gaussian wave packet. It falls freely in a linear potential. And here we can see that in fig B, that it accelerates, okay, and it gains momentum. However, it's tough to see it here, so we go to a space-time diagram, and here we see that the freely propagating Gaussian wave packet with a constant velocity, and here this wave packet is accelerating. So this is a proof of concept that really observed the acceleration of this wave packet in our system. Now let's perform Hilbert transform on these measurements and extract the phase. Now in blue, we see the GUI phase, which is this arctangents in the phase. Okay, and this is a really known result in optics. And if we apply the linear potential, we will see the full phase term here in red. And this is the first observation in history since Kennard solved the Schrödinger equation for Gaussian wave packet for the cubic phase. We go one step further and we subtract this phase from this one to extract the black phase. And the black phase is really just the cubic term extracted from this equation, and this is what is called the Kennard phase. Again, this phase appears for 91 years in textbooks, in papers on quantum cosmology, in optics, in undergraduate and graduate textbooks in quantum mechanics, and this is the first observation of this kind of phase. Now we're really intrigued by this good result, and we went to a more complicated case and wanted to see if we can measure Airy wave packets in our system. Now, an Airy wave packet, can you hear me like this as well? Okay. An Airy wave packet is a really interesting wave packet in quantum mechanics. Normally, if you take a particle with a constant velocity, it will propagate with a constant velocity, regarding as first law of Newton. But an Airy wave packet will self-accelerate. So imagine you have a particle, you put it, this particle doesn't feel any external force, and it suddenly begins to accelerate. This is what an Airy wave packet tells us. So we generate this Airy wave packet in surface gravity water waves, and in blue here, you can see that this Airy wave packet really self-accelerates without feeling any external force. Now, we apply an external force to the opposite direction of propagation, and we can see that we can slightly bend its self-acceleration. Now, Sir Michael Berry predicted in 1979 in his famous paper that if we induce a linear potential which is opposite to the direction of propagation of Airy wave packet, and it will be strong enough, it will cancel out its self-acceleration. It's a theoretical result, it was never measured before, and here I can show you it for the first time. We applied the linear potential, which is just opposite in the direction of propagation of the Airy wave packet, and we stopped the self-acceleration of Airy wave functions. This result gives us a soliton. It's a wave packet which is not spreading, and it keeps its shape while it's propagating, but this soliton is completely linear. So this is a new result of linear solitons, also relevant for optics and quantum mechanics. Now, if we look at the phase of Airy wave packets, the case is more complicated because we have a cubic term which results from nothing. The Airy wave packet accumulates cubic term because it self-accelerates. So this is the red term in the left side, and the blue term is the cubic phase that the Airy wave packet accumulates because it exhibits acceleration from the linear potential. So we really wanted to measure those phases. Of course, nobody has tried to measure them so far. And we succeeded at that. You can see in blue the cubic phase of Airy wave packets without external linear potential. And here we subtracted the cubic phase of Airy wave packets explicitly on the graph B. And when we induced the linear potential, we observed the addition of phases. The cubic phases arise from acceleration, and the cubic phases arise from intrinsic properties of Airy wave packets. So these results were recently published in our recent PRL, and then we looked at more recent wave functions, things that people publish in theoretical papers, and almost nobody reads them because there are no measurements of this stuff. And one of the most interesting cases we found is the quantum carpet wave function. Now, the quantum carpet wave function, derived from its name, it looks like a carpet. And the simplest way to create such a wave function is to sum some Gaussian wave packets, and then we will see interference effects between the lobes. So in right you see a theory, and left this is an experiment done recently in our lab. One step further, we went into the Archimedev-Breeder wave function. This wave function looks like this, and this is also an experimental result. Akhmedov also explored the nonlinear cases of this wave packet, so we increased the steepness, now resulting in a nonlinear propagation, which is analogous to optics, and many optics people do this. And we observed successfully a known theoretical case, okay, for the quantum revival at the middle disappearing. Okay, so again, this is a theory, and this is an experiment. And now we can really measure these nonlinear quantum carpets in our lab. We also tried to propagate these quantum carpets in linear potential, and we successfully observed that we can bend their curvature when we apply linear potential. Okay, and here you see this plot in 3D. This is without potential, and this is with potential. This result is really important because we can see that classical research on a classical surface gravity water wave system has encouraged us to write and create new wave functions for quantum mechanics and quantum optics guys. So we went from quantum physics to surface gravity water waves. We observed some wave functions that nobody saw before. Then we were inspired by it and created new wave functions that can be now measured in quantum mechanics, hopefully somewhere in the future. So I have 3 minutes. I will just tell you that we also explore black holes and plasma waves on surface gravity water waves. And I will talk very briefly about the analogy of a black hole in surface gravity water wave. So imagine we have an inversely harmonic barrier from an energy perspective view. And we have a wave packet approaching this barrier. In the first case, the wave packet will have a lower energy than the peak of the barrier, and then the wave packet will lose its momentum, and then it will be reflected to the other side. This is case number 3. If the wave packet has the same energy as the maxima of the barrier, it will eventually stop. This is case number 2. And if the wave packet will have a higher energy than the maxima, the wave packet will lose some momentum, and then it will propagate. Moving to phase space, which is momenta versus place diagram, we're creating this kind of diagram. So we have a parabola in the third case. We have a parabola in the first case, and we have a linear propagation in the second case. And this is a known diagram for black holes, and there's a lot of math behind it, but this is our way to generate now black holes on the surface of water, and we have some very nice preliminary results. So here you see a wave packet propagating along a direction, and then it encounters this parabolic potential here, and then you see no information going out for 1 second, which is equivalent to 1 Schwarzschild radius in Einstein's theory for black holes. Okay, this is a zoom in, and you can really see that there is no information there. This is a preliminary result. Now we're working on extracting the phase of these waves, hopefully to see a logarithmic phase, which is a quantity that nobody has measured so far in Einstein's general relativity. Now, I know that many of you didn't understand what I was talking about, so I prepared a poem, and hopefully this poem can summarize things better. Right? So we're surfing inside the untouched kingdoms and realms of the quantum physics core, measuring phases of accelerating wave packets which have never been seen before. Walking on quantum carpets through walls and barriers we propagate, only to see the unknown properties of their quantum mechanical fate. By inverting the quantum harmony of the scalable universe, we dive deep inside the black hole's radiation, for better or worse. Fate has determined that we are all equal before the quantum wave. However, to dive deep into the quantum realm, one must be wise and brave. This is everything, and you're welcome to ask questions.
Thank you very much, and for the creative summary. Question? A question?
Yes.
Yes, please.
What is the relation between the amplitude of your signal F and the artificial black hole you create?
Relation between the amplitude of my wave packet?
Yeah, the ratio between the black hole and the signal you send.
What do you mean by ratio?
What is the
What is the connection? Right.
no, what is the relation? Because like you can create a signal because you like, and you have to create a potential to absorb the information.
Yes.
How you define this?
So the group velocity, in hydrodynamics, the group velocity of the wave packet is the analog of energy in quantum mechanics. And the velocity, the derivative velocity of the homogeneous flow we have in the water tank is the analog of the energy barrier potential in quantum mechanics. So we have to fine-tune the group velocity of the wave packet in such a way that it will be equal in absolute value to the maxima of the velocity of the water which is coming from the other side.
Okay, thank you very much.
You're welcome.